So essentially what we're going to be doing now is we're going to be looking into how we can use our knowledge of trig identities and kind of trigonometric manipulations to determine certain limits that supposedly don't exist or that yield an indeterminate form upon direct substitution. So let's go ahead and do that. If we take a look at this first limit over here, we have the limit as x approaches 0 of 2 cosine x sine x divided by tangent of 2x. And so if we use direct substitution over here, we'll get essentially 2 times cosine of 0, which is 2 times 1, and then times sine of 0, which is equal to 0. So we'll have 0 in the numerator. And we're dividing by tangent of 0, which is sine of 0 divided by cosine of 0, which is yet again 0. So we have this indeterminate form over here. So what I'm going to do is I'm just going to erase this. Essentially, upon using direct substitution initially, we got this indeterminate form. So what we can do is we can see how we can manipulate it a little bit and see if we can get it such that it's actually defined, so it's no longer indeterminate. So the first thing I do is I look at this numerator and I see that we have 2 cosine x sine x. How convenient. Essentially, that just happens to be what you can say is the special identity for sine of 2x. It's the expansion of the double angle for sine of 2x, or for sine of x, I should say. So that's going to be sine of 2x. And then we're going to go ahead and divide that by tangent of 2x. Another way to write tangent of x, or just really tangent of anything, is just sine of x over cosine of x. So tangent of 2x is going to be sine of 2x over cosine of 2x. I know I'm writing these parentheses, it's very inconvenient. And then we can go ahead and multiply by the reciprocal, so we'll get cosine 2x divided by sine 2x, or multiplying that by sine of 2x. These two terms will cancel out very nicely, and we're left with cosine 2x. And so this limit is going to just be the limit as x approaches 0 of cosine 2x. So we can see this limit over here reduced very nicely into this significantly less intimidating limit that's actually defined. And so this is going to be equal to cosine of 0, which is in fact equal to 1. And so we were able to determine this limit using a little bit of very easy, actually, trigonometric manipulation, something too crazy over here. And so we're going to go ahead and use that same notion for these next two questions over here. If these questions look a little bit niche, it's because, it's quite difficult to find trigonometric functions that cancel out very nicely using the identities when we're taking limits. So my apologies if it looks a bit odd. But what we're going to be taking over here is the limit as x approaches pi over 4 of this very crazy rational expression that I'm not going to read out. We can use direct substitution, but spoiler alert, we're going to end up with 0 over 0. If we want to prove that, we'll get sine squared of pi over 4 minus cosine squared of pi over 4. We know that sine of pi over 4 equals cosine of pi over 4. So their squares are also going to be equal to each other, so we'll get 0 in the numerator. In the denominator, we'll have 1 minus the square root of 2 times cosine of pi over 4 is just the square root of 2 over 2. So that's going to be 1 minus, essentially we'll have 2 over 2, which is 1. So that'll be equal to 0, so we'll have 0 in the denominator. And so I'm just going to go ahead and remove this so we have a little bit of space to work here. And so essentially what we can do now is we can take a look at this numerator. Now the first thing I think is maybe how we can use the Pythagorean identity for sine squared of x to maybe manipulate this numerator a little bit. So we know sine squared of x is going to just be equal to 1 minus cosine squared of x. That's just our basic kind of unit circle or Pythagorean identity for trigonometry. And so we can replace this sine of x with essentially 1 minus cosine squared of x. So we'll get 1 minus cosine squared of x minus cosine squared of x. We're going to divide that by 1 minus the square root of 2 cosine x. And we see over here we'll get 1 minus 2 cosine squared of x divided by 1 minus the square root of 2 cosine x. And we can actually rewrite this expression over here as a difference of squares. It's not necessarily a perfect square, but we can write it as a difference of squares. So we'll get 1 plus the square root of 2 cosine x times 1 minus the square root of 2 cosine x. We're going to go ahead and divide that by 1 minus the square root of 2 cosine x. And as we can see here again, very conveniently, these two terms happen to cancel out. And we're just left with 1 plus the square root of 2 cosine x. So when we take the limit as x approaches pi over 4 of 1 plus the square root of 2 cosine x, That's just going to be 1 plus, again, we said the square root of 2 times cosine of pi over 4 is just 1, so that's going to be equal to 2. So we're able to determine that limit. And then as we move to this final one, this one is going to be a little bit easier. Essentially, if we input cosine of pi over 2, we'll be left with 0. Sine of pi, because essentially this is sine of 2x, so 2 times pi over 2 is pi. Sine of pi is 0. We'll be left with 0 over 0. And so what we can do now is we can kind of manipulate this a little bit. We have the sine of 2x in the denominator, so what I think to do is kind of expand it in terms of the double angle identity for sine. So here we'll have cosine of x in the numerator. In the denominator, we'll have 2 cosine x. Sine x. This term and this term will cancel out quite nicely. So we're left with 1 over 2 sine x. And then we can just use direct substitution, so we'll get the limit as x approaches pi over 2 of essentially 1 over 2 sine x, which is just going to be 1 over 2 sine of pi halves. We know sine of pi over 2 is just 1, so this will be equal to 1/2. And we're able to determine the limit quite easily. So essentially the whole point of this is just to show you that although the limit may not exist immediately, because there will be a point discontinuity or a removable discontinuity at the particular a value, as we saw for all three of these examples actually, if we use a little bit of trigonometric manipulation, we can see how we're very easily able to determine these limits, although they don't necessarily exist upon immediate direct substitution. So the point is, whenever you're given some crazy rational kind of rational expression containing trig functions, then see how you can manipulate it first before you actually try to take the limit.